Hello. So today I'm going to be giving an overview of the motivation behind using electromagnetic induction for energy efficient processing, and I'm going to quickly cover some of the current challenges and solutions that we have to this process. There we go. So current conventional composites curing methods such as autoclave, oven, as well as hot press systems are very inefficient in terms of their energy usage. This is largely due to energy being wasted heating consumables, surrounding air, and tooling that has very high thermal mass. The application of heat in these processes is generally conduction from the surface of the material, and then you have to wait for a thermal lag for the heat to enter the center of the laminate. Induction heating is a highly energy efficient, direct, volumetric and non-contact heating method that's capable of very fast heating rates. Electromagnetic induction and heating occurs in electrically conductive or magnetically susceptible materials in the presence of an alternating electromagnetic field. For composites, carbon fibre is itself sufficiently electrically conductive to be able to produce internal eddy currents, and therefore heating, mainly due to resistivity of the fibres, known as Joule heating, as well as contact resistance at conductive fibre junctions. The image on the left is the setup that we have in the lab, along with the pancake coil, which is very standard coil geometry, commonly used in metallic processing. I'm going to show you a quick real-time video that demonstrates the rapid heating rate that can be produced using induction, using this coil in a quasi-isotropic carbon fibre panel with no additional materials required. The rate of heating is solely dependent on the current flow passing through the coil itself, and the rates that we can achieve are significantly higher than is possible in other conventional methods. I'd then like to draw your attention to the other key fundamental advantage in induction, aside from the rate of heating, which is that the heat is produced volumetrically. This means that heat is produced within the fibres themselves. So the panels that we heat are heat is generated from within the panel rather than from the surface in these alternative methods. So this leads us on to what's the key challenge preventing access to or accessibility of induction to a wider scale of uses. And that currently is the in-plane temperature non-uniformity. If I draw your attention to the heating image on the right, is a still during heating. What we can see is that we have this central heating ring and a temperature difference of as high as 65 degrees between 2 points that are only 10 centimetres apart. So this is significantly limiting in terms of our manufacturing capabilities. And this is where my research is currently focused, is looking at improving the macro scale uniformity. I'd like to sort of finish today's talk by identifying one of the potential routes of research that I've been conducting, focused around redesigning of an induction coil specifically to account for the properties present in composites. So what we have shown in the bottom left here is a novel cellular structure designed to induce localized electromagnetic vortices and small regions of heating to reduce the reliance on in-plane thermal conductivity to spread the heat and improve the macro-scale temperature uniformity. On the top we have a selection of differing panel sizes with experimental heating using this novel coil, and below some finite element modelling that I've conducted that's going to in the future be used to improve and optimize this coil design. Thank you. you have any questions?
Thank you.